function approximation and the Remez algorithm. Hello everyone. This lesson provides definition of Remez algorithm as well as its implementations. It also includes some examples for each concept introduced. On this lesson, you will learn about overview of minimax approximation, Remez algorithm, procedure and discussion, and Sebastian notes. Sebastian notes, as mentioned in the introduction, the location of the interpolation points is an important consideration in polynomial approximation. Intuitively, one might accept that equispaced points in a given interval are ideal for polynomial interpolation. The solution for these problems are the Sebastian notes. Given a function f in the interval ab n points x0, x1, xn and the interpolation polynomial pn, the interpolation error at x is given by function e of x for some summation in interval ab. If we want to minimize this error, we don't know the function f nor can we specify the value of summation. So in minimizing the error, we consider the minimization of gamma I equal to 0 to n x minus xi. Sebastian notes minimize the product above, as we will see in the next section. When one has the flexibility in picking the interpolation points, the Sebastian notes are ideal. In an interval AB for an polynomial interpolant of degree n minus 1, the Sebastian notes are given by this xi function. The Remez algorithm for approximation function. The Remez algorithm is due to a Russian mathematician Remez, who published the result in 1930. It is an efficient iterative algorithm that computes the minimax polynomial. To initialize the algorithm, we need a set of n plus 2 points in the interval AB. One could choose different initial points, but a common choice is the Sebastian node. This is because, as we discussed earlier, the Sebastian nodes are not prone to the rank phenomenon and minimize the interpolation error. Hence, the polynomial that passes through the Sebastian nodes is a good initial estimate for the min-max polynomial. Let the polynomial Pnx passing through the Sebastian nodes be the function Pnx, where b0, b1, b to the power n are the coefficients. Now, we want to force the oscillation criteria on this polynomial. That is, we want the error between the polynomial and the function. The function f to oscillate alternatively at the Sebastian nodes. For that, we will write the system of equations below. We can write this in a matrix form as follows. We can solve this n plus 2 into n plus 2 system to find the coefficient of b0, b1, n. The Remez algorithm in Python, the main steps are: for a given function fx on an interval ab, specify the degree of interpolating polynomial. Compute the n plus 2 Sebastian points using x0, x1 to xn plus 1. Enforce the oscillation criteria by solving the n plus 2 system of equations. We get here b0, b1, bn plus 1. And from a new polynomial Pn with above coefficient, we can get Pnx equal to b0 plus b1 x1 plus bn x to the power n. The step 5 is compute the extreme of the error function Pnx minus fx. This will give a new set of control points x0 power, x0, x1 power, xn plus 2. Uniformly on interval of AB, if f is real, the Pn may be taken. Conclusion: we see that Remez algorithm is an efficient method to construct the min-max rational function in the approximation of a discrete set of data. It takes few iterations and does comparably better than a nonlinear optimizer like SLSQP. However, it is not always the case that, unlike the case for polynomials, the process of finding rational functions does not always converge. But for most common functions, the Remez algorithm leads to a good approximation. Thank you, everyone.